All right, so this question, the student said, I am confused about how to calculate the t. Now, I'm not exactly sure if he meant the test statistic because for certain problems we do have t distribution where the critical value would be a t-score and the test statistic would be a t-score. But I'm going to assume that he meant calculate the test statistic, which actually in this case would be a z-score. Because we're doing a test about a claim about a proportion. And proportions, we always use z-scores. The only time we ever use t-scores is when we're doing a claim about a mean with sigma unknown. So this is a claim about a proportion, so we'll use the z-scores for this. Okay, but if his question is how to calculate the test statistic, let's focus on that. So the test statistic, what is it? What is a test statistic? Well, it's where you take your sample statistic and you turn it into something that can be compared to the critical value. So for this problem, our critical value for this left-tailed test would be to the left of 0 on the z-score scale, somewhere over here, a negative critical value that is a z-score. And we have a sample statistic given in the problem here. Let's see, right here. This and this give us our p hat. That's our sample proportion, which is the number of successes out of the number of trials. Oh, it's a 7. Okay, so that'll be our proportion from the sample. And we're testing that against this default assumption that the proportion is 0.51 for the whole population. And we got this result from a sample, and we're going to see if that seems like it could have happened by chance, or if maybe the null hypothesis is incorrect. So we want to know, where does this proportion lie in relationship to the center, right? So our population proportion of 0.51 is there in the center, and our population proportion, which would be, or I meant to say our sample proportion, which would be, let's calculate it as a decimal. So p hat here would be 336 divided by 747. And the claimed p hat, or the p hat in our null hypothesis, is 0.51. So what I want to know is that really extreme compared to what we thought the population proportion is supposed to be? So 0.45 is somewhere over here, right? 0.45. So here's my population proportion P, and P hat as a z-score is what we want to know, because I know that 0.45 is less than 0.51, but I don't know how much less it is in terms of standard errors. And I need to know that. I need to know the z-score to know if it's really significantly different. So I'm going to find that test statistic. I'm going to convert my p hat into a z-score. So p hat gets converted into a z-score using the formula right here. Z equals p hat minus p over the square root of pq divided by n. So that'll be 0.4, what was it, 0.45? 0.45 minus 0.51 See how far apart those are, and then how many standard errors would fit into that. Standard error will be P, which is 0.51, times Q, which is 0.49, and divide that by 747, and all of that is inside the square root. So let's calculate the test statistic. Probably should have cleared out all these other values because this is from another example. Should we go through and just do the whole thing? The claim is that the proportion is less than 0.51 for the population. We have this default assumption that it's equal to 0.51. So the alternative hypothesis actually is our claim since there is no equality in the claim. That means that since our claim is in the alternative hypothesis, if we reject the null, we will support the claim. We have a left-tailed test and we're using z-scores because it's a claim about a proportion. The significance level is 0.01. And the area to the left would be 1 minus that, or no, that would be if it was on the right. Since it's on the left, it's just straight up 0.01. And the z-score there, the critical value, will be negative since it's on the left of the 0 there as a z-score. So I'll use norm.inv on the left area with a mean of 0 and a standard deviation of 1. So now we know that we have on the, as far as the critical value is concerned, negative 2.326 has an area of 0.101, 0.01 to its left. Okay, so this is our goalpost, this red area, this red region. If our p hat is far enough away from the center all the way into the red tail, then we will reject the null hypothesis. It will be a significant result. However, if it's outside of that, it will be an insignificant result and we will fail to reject the null hypothesis. So let's calculate that test statistic here. It's going to be negative because my p hat is below the proportion p, so negative. And the value we will calculate using p hat minus the population proportion that we're assuming to be true unless proven otherwise, or unless evidence is presented that convinces us it's possible that it's not. And then you can do your square root of p times q. Remember, q is 1 minus p divided by your sample size. Okay, so there's our critical value. Now that is more extreme than the critical value. Or I meant to say there is our test statistic, which is more extreme than the critical value. So we will reject the null hypothesis here because our p-value, or I meant to say our test statistic, our p hat has a z-score that's more extreme than the critical value. And this p-value over here, that's the probability of this happening by chance. And that we will find by using norm.dist on the critical value. Said the wrong thing, I meant the test statistic. The mean of 0 and the standard deviation of 1. Cumulative. So a very tiny p-value, 0.0005. So it's extremely rare for this sample proportion to happen just by chance, which means that maybe this population proportion isn't quite right. Okay, so we would say the test statistic is more extreme than the critical value, so reject H sub 0. We would also say, by comparing the areas, that the probability, the p-value, is less than alpha, so reject H sub 0. And the claim was part of the alternative hypothesis, so by rejecting the null hypothesis, we have support for the alternative. So we say the sample data support the claim that, and then you fill in the blank. What was it? The probability of catching the flu this year. The probability of catching the flu this year is significantly less than 0.51.